All right, it is time for Lesson 9. Lesson 9 is all about the derivative treated as a function, because in our last lesson we took a look at how to find a derivative, and it's fine to find derivatives, but we find derivatives at specific numbers. And by finding derivatives at specific numbers, you got to do that over and over and over again, even if the function is the same. So in our lesson today, we take a look at, okay, can I treat this derivative as a function so that if the function in question stays the same, then the derivative, we just find that in general, and then we can find slopes of tangent lines at specific places just by plugging in numbers. The definition from Strang's book. Let f be a function. The derivative function denoted by f prime. This is f with an apostrophe. It is read f prime. Is the function whose domain consists of those values of x such that the following limit exists. F prime of x is the limit of f of x plus h minus f of x over h. That's that familiar difference quotient as h approaches 0. It is identical to the definition of slope of a tangent line because derivatives are slopes. Derivatives are slopes. Couple of vocabulary words here. A function is said to be differentiable if it has a derivative. So we don't talk about derivatizing. We talk about differentiating. We don't talk about derivatizable. We talk about a function being differentiable. A function is differentiable on S if it is differentiable at every point in S, and a differentiable function is one in which f prime exists on its domain. I'm going to do a couple of examples. Strang also has a couple of examples in his book on PDF pages 240 and 241. They are worth a look, particularly if mine are not helpful. Couple of examples for us. If f of x is x squared plus 6x plus 4, find f prime of x. This is the process of differentiating f of x. We are finding the derivative of f of x. So the derivative of f of x is the limit as h approaches 0 of f of x plus h. Well, what is f of x plus h? That's what happens when we replace this with x plus h and this with x plus h. X plus h squared plus 6x plus h's plus 4. F of x plus h minus f of x. Well, minus f of x, that's f of x. And we're going to subtract that. And we're going to remember that when you subtract a polynomial, you subtract each of the terms over h. F of x plus h minus f of x over h. So the rest actually turns out to be just algebra. We'll expand the brackets, x squared plus 2hx plus h squared. Hope that algebra is okay for you. If not, you should definitely be pausing this video to consider that. I mean, it does pause. You can pause it. The rest is algebra, and if you're comfortable with that algebra, then you are also comfortable with those are the same, and those are the same, and those, well, they just go. So what's curious is that what's left, this has a factor of h, 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 and so by simplifying, we just remove the factors of h and divide. And then as h approaches 0, this is unaffected. This doesn't care what happens as h goes to 0. This does. As h goes to 0, h goes to 0. Nothing to write here. And then as h goes to 0, 6 is still 6. That is the derivative. So if this is my function, this tells me how to find the slope of the tangent line at any particular x value. This is the function. This tells me how to find the slope of a tangent line to that function at any point. One more. If y equals 1 over x, find, this is red dy dx. This is Leibniz's notation for a derivative. This is Leibniz's notation. And Leibniz's notation reminds us that a derivative is a slope. You learned when you were much younger that slope is delta y over delta x. It's a change in y over a change in x. Leibniz uses this notation, well, used this notation. He's dead. Leibniz used this notation for derivative because he wanted to remind everybody that a derivative is a slope. So he gave it a notation that is similar to the slope notation. So how do we do that? Well, dy dx, that's how it's read, is the limit as h approaches 0 of f of x plus h, which means we sub out all the x's for x plus h's, minus f of x over h. And we think to ourselves, why can't we just throw 0 in for h? Oh yes, that's 0 over 0, that's a problem. And so what do? Well, in this case, I'm going to combine the fractions in the numerator over a single denominator. That single common denominator is x times x plus h. How do we combine fractions when the denominators are different? Well, this gets multiplied by 1, and this gets multiplied by 1, and it gives us that common denominator. So this is x, this is minus x minus h. X minus x minus h. The h's drop out, and so you have the limit as h approaches 0 of negative 1 over x times x plus h. Well, what's that? As h gets closer and closer to 0, this doesn't care. As h gets closer and closer to 0, this doesn't care. As h gets closer and closer to 0, h gets closer and closer to 0, this gets closer and closer to x plus 0. And so this is negative 1 over x squared. This is the function. This tells me how to find the slope of the tangent line at any given point. So, if I may, I'm going to graph some things. Let's graph some things. If I can, let's graph the thing that you had in example 1. This is a parabola. And we can probably put this in the standard viewing window. Yeah, that's what it looks like to you. And let's graph its derivative and see if we can notice anything. So this is the function. This is the derivative of the function. What do we notice? Well, we notice that our function goes down and then it goes up. Our function goes down and then it goes up. It stops going down right here. What's true about the derivative there? Well, the derivative is 0 there, and that kind of makes sense. That's a flat tangent right there, and a flat tangent has a slope of 0, so we would expect that the slope function is 0 right there. As the function is going down, we're going to call that decreasing. Its derivative graph is negative. All of these derivative values are negative. They're below the y-axis. And then when the function starts increasing again, the derivative goes positive. So where the function is increasing, the derivative is positive, and where the function is decreasing, the derivative is negative. And I wonder if that's a thing. I'll turn these off for the moment. let's consider the other function. The other function was 1 over x, and its derivative was negative 1 over x squared. So the brown is the function, and the blue is its derivative. Well, that brown function is always decreasing, and its derivative is always negative, always negative. The blue derivative always lives below the x-axis. All of its values are negative. So there seems to be a connection between a function decreasing and its derivative being below the axis being negative. And so that's something we want to keep tucked away in our mind's eye. I've got a quick OYO for us to do, something that we're going to want to consider before we gather. You should know how to do the algebra. You should find g prime of x if g of x is x squared plus 4. You should know how to find a derivative. You should also, if this is some function h, you should be able to sketch a graph of h prime, using the fact that when this function is increasing, its derivative should be positive, and when our function is decreasing, the derivative should be negative, and when our function is increasing, the derivative should be positive. One other quickie to get in before our 15 minutes are up. I want to say a quick word about higher order derivatives. And all higher order derivatives are derivatives of derivatives. If we take the derivative of the derivative, that's a higher order derivative. So if you have some function f of x, its derivative is f prime of x, but the derivative of f prime of x is f double prime of x, and the derivative of f double prime of x is f triple prime of x, and at that point we stop writing primes. If we go to a fourth derivative, we write the 4 in parentheses as an exponent, and that is understood to be the fourth derivative, the derivative of the derivative of the derivative of the derivative. In Leibniz's notation, if you start with some function y, then the derivative is dy dx, and the second derivative is written this way, where the power is on the d up here, and the power is on the x down there, and similarly for third derivatives and fourth derivatives, and so on. So, why do I care? Suppose we have a position function. Position is usually denoted with s. Suppose the position function is 5t squared plus 3t plus 2. This allows us to find the position of a particle at any time. Find the acceleration function. Well, how do you get to acceleration from position? First, you find velocity, because the derivative of position is velocity. Velocity talks about how position is changing over time. So the derivative of position is velocity. How do we do that? Well, that's s prime of t. That's a limit as h approaches 0 of our function at t plus h minus our function at t. Remember, everybody gets subtracted over h. And I'm going to let you do the algebra on that to confirm that you do in fact get 10t plus 3. You should confirm the algebra for that. Expand the brackets, cancel some things out, factor out an h. Pause the video if you have to. Then what? Well, then we find acceleration. Acceleration talks about how velocity is changing over time. How is velocity changing over time? Well, that's a limit as h approaches 0 of how velocity is changing over time. So we put our t plus h's into the velocity function, minus the velocity function, everybody gets subtracted, over h. And I'll leave you to confirm that that does in fact turn out to be 10. If you're looking for extra practice, and you probably are, in section 3.2, you want to look at 55 and 57 and 65 and 71 and 79 and 99. Our 15 minutes are about up. Thanks for sticking with me. We'll see you in class.